All right. Got any questions?
How are you?
Okay. Got any other questions? No, and just got an email that the employee Wi-Fi is down, which I noticed this morning. So I just ordered a Cat 5 cable from Amazon. Yeah. So I'm officially off Wi-Fi. I have a fast flash drive, so I can dump things onto a flash drive. So hopefully I can upload these after class, as long as my cable works in my office. Should be able to do that.
Yeah, my question is related to PA1.
Okay.
Okay. My question is, for like functions like delete and search, is it okay? Like, what's the difference between a for loop and a while loop? Search through the node, and a while loop to use a for loop.
You can't really use a for loop to do your search function, because a for loop is really when you want to loop a certain number of times, basically. And we don't know up front how big our list is. And you're not searching the array in your search function, right? You're not just going through each node looking for your number. You're following the nodes from the sentinel to the next node to the next node and looking to see if the value matches the one that you are looking for. So that's probably some kind of while loop. Okay, cool. My theory is that when class ends, everybody takes out their phone and the network crashes, and then a minute or two after class starts, people put their phones away and the network recovers. Because like at 8:50 and 7:50 and 9:50, everything kind of goes south. So, but I don't know, it's just a theory. All right, does that make sense on PA1?
Yeah, so it's better to just do a while and then update it every time.
Yeah, so your goal, like I say, you have a sentinel node. And you've got a list and it's sorted and you're searching for a number n, right? Start with the sentinel. Okay, the sentinel, you're allowed to use the knowledge that this is element 0 in your array. So see what the next field is. If it's not null, go to that element in your array, see if the data matches what you're looking for. If not, look at the next field. If it's not null, go to that element in the array, see if the data matches what you're looking for. So you're really following this link of nodes from one node to the next, and at each point check to see if the data matches what you're looking for. So it's either while, it's probably a while the next thing is not null, because that's when you know you're at the end of the list. If this thing is pointing to null, or my null, then you know you've gone through the whole list, and at that point you can kick out of your while loop and just return 0, I didn't find it. And inside the loop, if the data matches what you're looking for, you can just return a 1 right there. Do you have your hand up?
Yeah, I did that with for loop, but I just had my exit condition be if as long as your current index is not equal to the my null.
Yeah, but why would you do it as a for instead of a while then?
Yeah, that's my question. Is why? So I think I tested my search function and it seems to be functioning the way it's supposed to.
Okay.
So the way I did it was I said, for instance, your I equals your sentinel node dot next.
Okay.
And as long as I does not equal my null, then your I equals your linked list sub I dot next.
Mm-hmm.
So that's how it's updated. And then if your data or the industry got passed is equal to the data field in your current linked list, I'm returning 1.
Okay. So that sounds right. And you can do a while loop with a for statement, right? But it's not something people usually do,
Okay.
right? If you really want to, so think about your flow chart. right? If at the bottom of this you want to perform some operation and you want to test to see if the result of that operation satisfies some condition, right? And you also want to do some initialization, that's a pretty natural structure for a for. But it's probably less confusing if it's just a while.
Do you care if we can like add multiple, like if we add 25 twice and it shows up twice on the list, or do you want it so you can only add a number once?
I want it so you can only add a number once. And just call your search function before you add. And if it's in there, just print a message saying it's already in there. Because that's definitely a case I'll test. Personally, I try not to be dogmatic about style for the most part, but there are things that I think will raise eyebrows, like for I semicolon, I less than 10, I plus plus. Right? That's going to raise eyebrows if somebody sees that at an interview or in another course. Initialize your variable here, or if you really don't want to do anything, just say for semicolon if there's really no initialization you want to perform. But chances are you want I to have some starting value. It really should go in that first part of the for statement. Right? That's going to work fine for the compiler, but that's really just a while statement. It's saying I don't have any initialization, I don't have anything I want done at the end of the loop, so basically as long as x is not equal to y, keep doing this loop. That'll work perfectly fine, the compiler has no problem with it, but it'll raise eyebrows, and at some places it would cost you points. Right, I think I told you in 224 I had a student at UW, he lost points because he said for j equals 0, j less than 10, j plus plus, and the teacher said I is the traditional variable for outer loops. And he lost points because he used j. Now UW has like a 30-some page, I think it's 30-some page style guide that describes all of these things that you should adhere to when you write your code. Stuff that doesn't affect the behavior, but it affects the style. And most places that you do programming, they have a style guide that they expect you to adhere to. So should your curly bracket go at the end of the if, or should it go down on the next line? Should the curly bracket be indented, or the thing following the curly bracket be indented? People care about that. Compiler doesn't care. But people care about it. And in industry, you probably have a tool that's doing the formatting for you. They've already set it up. You're using Eclipse or something. But if you're just writing code barehanded, sometimes you have to conform to a certain structure of the layout of your program. So I don't worry about that myself in here, because I want you to concentrate on what the code does. But I want to at least mention that there are times where you'll have to code a certain way.
Is there like an industry standard, or is it just sort of vary?
I think there's a bunch of industry standards. That's the problem. There's probably a best practice somewhere. I don't know if it changes over time or what. But you can Google it and find all kinds of examples, and you can get UW's style guide from their website, and it's a pretty good representative of the kinds of things that you'll see elsewhere. So let me talk about ODP 205. This was the first ODP where we were using a pointer to a struct node, and I suggested playing around with the arrows to dereference the pointer. And some people did that. But I looked at the code on this, and some people were able to get full credit but do something very unusual in here. Struct node star kind of looks like an array. So here's some of the quirky things that C brings along with it. So PTR is a pointer to a struct node. And if I want to access the thing it points to, technically I should do that. And if I want to access the field called data, I can do that. And we have this shorthand, which lets us say pointer arrow data. But if you were to do pointer bracket 0, that technically does the same thing as this. It says pointer is an array of struct nodes, give me the first element. Well, that's going to be the node that pointer is pointing to. Technically, that does the same thing as that, and technically, this does the same thing as that. But unless you really know that you're getting an array, don't do this. If you just want the thing that pointer points to, do this and this, or best of all, do that. Again, to the compiler, it's the same thing, but if you do this, you risk thinking that you're actually dealing with an array, and at some point you're going to be tempted to say this, or pointer bracket I, and that's segfault time. So stick to that, or ideally, if you're dereferencing and using a field, use the arrow notation. So so here's my set function. I did not need standard io.h in the top. I don't know why that's in there. You only need that if you're doing things like print, scan, ff, gets, and so on. So there's the struct node definition, and then the set function is 2 lines of code. Take the pointer to a node, pick off the data field, multiply by 2, assign that to the data field, and then set the next field to null. And when you're dealing with pointers, stick with null. Okay, try to avoid using 0, using quote \0 or other things like that. Stick to null. Because null is defined to be a pointer. I think it's a pointer to a void technically. To a void, not to a void. To a type void. And if you do this, you'll get at least a warning. And if you do this, you risk possibly not actually setting it to 0, because this is only a single byte. And this is actually only 4 bytes, and pointers are usually 8 bytes. So null is the right thing when you want to have it point to a 0. Use null uppercase. That's why I included standard io.h, because that's where null gets defined. I can never find these things in here. Somewhere in this string of inclusions, the symbol null is defined, though. So if you want to know what null is, we can just print it out with a print statement. We have to ignore some warnings. And null is 0. But it's a particular type of 0 that keeps the compiler from giving you warnings. Alright, so does that make sense, set function? That's basically the code we had yesterday. Alright, so today's function, you're writing a function that gives you a new node, and this can be part of PA2. So the same struct node that we're going to be dealing with in all of these next few ODPs. So new node takes an integer and returns a pointer to a struct node. And the behavior is it creates a new node, it sets the data field equal to that data argument, and it sets the next field equal to null. So it's kind of like the get node function, but it's also initializing the data field. And when we repeat PA1 using this kind of struct node, when you want to insert into a list, you're going to have to create a new node, set the data to the right value, set the next field to null. That's what your new node function is going to do. And unless you're inserting at the end, the next field will get changed to point to whatever the following node is. But for this one, I want you to always set the next field to null, just to give it a fixed value. All right, so any questions on 206? So you have to use malloc, and then you have to set up two fields. So the code itself is probably 3 lines. So we talked about malloc yesterday. So let's say PTR is a struct node pointer. And we want to create a struct node and give it some values, for example, to return from this new node function. So we use this thing called malloc. And you have to tell it how much space you want to allocate. And since we're allocating something that's going to point to a struct node, we want enough space for a struct node. So we can say size of parentheses struct node. And malloc will return a memory address. And if we assign that to pointer, pointer's now pointing to a block of memory that's big enough for a struct node but hasn't been initialized. So you can do pointer arrow data, pointer arrow next, and so on. Now what happens if the machine runs out of memory and we call malloc and we ask for a chunk of memory and there's no memory left? Any idea what malloc's going to return? It's going to return null. Okay, just like your get node function returns my null, malloc will return null. So theoretically, anytime you call malloc, you should check to see if pointer is null. And if it is, you're out of memory. But it's very unlikely you'll run out of memory unless you have a problem with the program, if you've got some kind of malloc loop going. So the flip side of malloc is free. Malloc finds a chunk of memory, gives you the address of it. When you no longer care about that chunk of memory, when you're not going to use it anymore, you'd like to take that space and make it available to the system for someone else to use. And so the call free lets you give it the address of something that you malloced, and it basically updates its internal structures to say, okay, this block of memory is free now. This is like your release node, like setting the valid flag back to 0. So malloc gets space, free releases that space. And it's really important that you free whatever space you allocate when you don't need it anymore, especially if your program is going to run forever. Because if you allocate space and you use it and someone says, let's delete a node, and so you remove it from the list, but you don't free that space up, you've only got 10 things in your list, but you've got 11 nodes allocated in memory. And now they insert 1 million nodes and they delete 1 million nodes, and maybe your list is empty, but now you've got 1 million nodes allocated in memory that aren't being used. And once you change the links so they're not pointing to those nodes anymore, you have no way to get to those. So they're lost. And if you've lost a reference to a chunk of memory that you've allocated, you cannot free it. It's permanently lost until your program exits. Now once your program exits on Linux, all the memory that you've allocated gets reclaimed and goes back into the free memory pool. But if your program never exits, like if it's a web server and it's supposed to run forever and it's been up for 5 years, it's just chewing up more and more memory. And eventually you run out of resources and your machine will crash. So that's called a memory leak. Memory leaks are when you are losing memory as your program runs. Not losing it because you're using it, but losing it because you're not releasing it when you're done using it. And memory leaks are very common, very easy to have. Certain browsers for a while were notorious for having leaky memory. So you'd keep your browser open for a few weeks and your system would just get slower and slower and slower, and it's because that piece of software was allocating memory and it wasn't releasing all of it. And over time, the system would run out of memory. So you could exit and restart and everything's back to normal, but that's a pain. So we'll talk more when we get into PA2 and PA3 on how to find leaks and how to deal with them. There's tools we can use, in particular a tool called Valgrind, which will watch our code while it's running, and at the end of our program it'll tell us if we lost any memory. And with PA2 on, we'll start using Valgrind to make sure we don't have memory leaks. And it's just a good practice. All right, I don't think I did this in here. I think I did in the afternoon section. The thing I said would be a really good test question. I don't think I did it in here, so let's do this in here. So this has to do with stars and ampersands, right? So I want to dig down into what that really does. So star variable means the thing to which variable points. And ampersand variable means the address of that variable. So ampersand var tells me where is this variable stored in memory. And star variable says treat variable as an address. Tell me what's at that address. So if variable is equal to 100, star variable says what's at memory location 100. Variable itself might be stored at location 15. Ampersand variable would give me 15. That's where in memory variable is stored. And these are complementary operations. So let's play with these. Let's make a memory map. So here's our memory. So here's the address in memory, the location. Here's what we're using it for, and here's the contents. So suppose I say integer I, and the system needs to decide where in memory am I going to store I. I've got to put it somewhere. Let's suppose it decides it's going to store I at location 10. So this is where I is stored. Do we know what its contents are yet? We got no idea because we didn't initialize. We didn't say integer I equals something. So the contents, no idea. Okay, now we're going to say integer j equals 10. So the system says, okay, I got to store j somewhere. Where should I store it? I can't store it at 10. I'm using that for I. I'll store it at location 20. So we'll use this for j. And we do know its contents because we said j is equal to 10. So this has got a 10. And then let's have an integer star pointer. And you can guess where the system wants to store that. Let's go ahead and put that at location 30. And we don't know where that's pointing. Okay, so this is a memory map, right? The use column is just for us, just to remember what we're doing with these locations. But location 10, don't know what it has. 20 has a 10. 30, don't know what it has. That's what the memory might look like after these three statements. Okay, so now let's do I equals 20. So what is that going to change in our memory map? Say again? Yeah, so right here, right? This is going to change to a 20. Okay, and this was the thing I said would be a really good exam question, so that's a hint. Okay, so that puts a 20 in this location 10. So now let's do something like PTR equals address of J, ampersand J. So ampersand variable means the address of the variable. So we're asking for the address of J. Where is J stored in memory? J is stored at location 20. The fact that it's got a 10 stored there doesn't affect anything. We're asking for the address of J, that's a 20. So this basically says pointer equals 20. So pointer is stored here at location 30, so that writes a 20 right here. Okay, now we say star pointer equals 5. What is that going to do?
Will that make the contents of J become 5?
That will make the contents of J become 5. So the right-hand side is just a 5. The left-hand side says I want the thing to which PTR points. So it looks at PTR, now it looks at the value of PTR, that's a 20. So star pointer is basically star 20 equals 5. In other words, the thing at memory location 20 should be set equal to 5, which is basically saying J equals 5. So that's going to put a 5 in here. All right, what if I say star I equals PTR?
Will it give me an error?
Compiler will give me a warning, but at runtime this will work fine. So if we ignore the mixing of data types.
So change PTR, the value of I, the contents of I to the PTR, which is 20.
So PTR is 20, so where is it going to get written in memory?
The contents of I.
Well, if I said I equals PTR, definitely.
It's going to change J's contents.
Yeah, so I contains a 20. Star I says the thing to which I points. I is equal to 20, so star I is the thing at memory location 20. It's this box right here. So this is saying set this box equal to PTR. That's going to put a 20 right here. Yeah?
What if you said star I is equal to J when it used to be equal to 5?
So let's go back to 5. Star I equals J. So star I is this box right here. set it equal to j. J is 5, so it's going to write a 5 there. So it won't change the value.
Alright.
All right, star ampersand I equals 100. I can do this all day.
It's gonna change the contents of I to 100.
Okay, why?
Because the ampersand says the address of I. So the address of I is 10. Change the contents of that address to 100.
Okay, perfect. So ampersand I is the address of I. That's a 10. Star 10 is this box right here. So set that box equal to 100. And that's just a long-winded way of saying I equals 100. Address star pointer equals 200. This is a little weirder. Pointer is equal to 20. Star pointer is j. Address of j is 20.
Change the address.
Yeah, so that's going to be a weird thing to do.
I'm guessing compiler would then do.
I think compiler will stop you in your tracks. We should try it though. So ampersand and star kind of do complementary things, but this makes perfect sense. This is finding the address of something and then taking the thing pointed to by that address. That I think is going to, it might give you PTR. Well, let's try it. Why not? Yeah, it doesn't like that. Even if it did like it though, there's a good chance that this would give us a seg fault. So yeah, let's do the seg fault ones now. Let's do star j equals 15. So what is this asking the system to do?
Go to the address 5.
Say again?
Go to the address, is it 5 now?
Yeah, j is equal to 5.
So go to the address 5 and change the contents at address 5 to 15.
Right, so go to address 5, which is somewhere up here, and change the contents to a 15. Is that going to work? I don't know. I don't know if 5 is accessible. If it's accessible and writable, then it will store a 15 in that location. But if that location is not accessible by our process, we'll get a seg fault. And so typical example is when j is equal to 0 and you try to do star j, you get a seg fault because you're asking for memory location 0, which usually is inaccessible.
Say you have multiple programs running at one time.
Mhm.
All the programs are running, if they block out memory, is that reserved for use of only that program?
Yes, on say a Linux system or a Windows system, yes, because these systems have what's called virtual memory. So on older systems, you had just physical memory, so you've got memory locations that are consecutive, and if this process grabs this block of memory, that's reserved for that process. But if another process were to request something at the same address, it would pick up that data that this other process is using. On a modern system, everything is virtualized, so there's a virtual memory space just for my process. And when I access location 20, And you access location 20, we're actually pointing at different locations in the physical memory. So it simplifies a lot of the implementation and a lot of the security issues. Memory mapping is like a whole area in itself, and it's pretty fascinating, the levels between the cache memory and, well, now the cloud. There's this whole hierarchy of storage. All right, so ampersand and star, right, until you sort of mess around with them and get used to them, they sound pretty weird, particularly this star thing. Ampersand's fairly straightforward, it's just where the variable is stored. But star, it's an indirection. Okay, it's saying I don't want the value of variable, I want to treat that value as an address, and I want the value stored at that address. Okay, this is the indirect file register in 270. It's exactly what this is doing. And it's how we do everything on computers. It's how arrays work. It's how structures work. All right, so questions on that? So let's go back to linked lists. So our nodes are going to have two pieces, a data piece and a pointer piece. We don't need a valid flag because we're using malloc to get memory and we're using free to release it, so we don't have to keep track of elements in an array. So we just have a data piece and a next piece, so it looks like the blocks we're drawing pictures of. We're still going to have a sentinel node. And the sentinel, we still don't care what the data value is, so give it your favorite number. And initially, the next field will be null. And again, it's NULL instead of 0 or MyNull or -1 or something like that. And so this is an empty list. Contains just a sentinel. So creating a new node, that's your ODP 206. So you'll figure that out if you haven't already. So let's do a print. Well, let's look at main first. So our linked list is still going to be a struct node star. So this is the linked list. And we can call an init function that returns the sentinel node. So malloc a node, set the data to whatever you want, set the next to null, and return that value. Have we talked about returning pointers? Do you want to go over returning pointers? Okay. You'll do this in your new node function. This may be ODP 207, I don't know. If it is, you get it for free. So let's make an init function that returns a struct node pointer. So we have to define a struct node star in here. We have to allocate space for it. So how big should we allocate? size of struct node. And be careful with this. We don't want to do size of struct node star. Because struct node star is a pointer, size of struct node star is the size of a pointer, that's 8 bytes. We're not trying to allocate space for a pointer, we're trying to allocate space for a node. So we have to say size of struct node, even though we're storing that return from malloc into a pointer. The thing it's pointing to is a struct node. If that node has 1,000 bytes to it, we want to allocate 1,000 bytes. So size of just bare struct node. So set the data value to whatever you prefer. Set the next field to null. And then, what do we return? What would you hope we could return? Yeah, temp. And that actually works. Why does that work? Because temp is just an address. It's an 8-byte number. No problem returning 8 bytes. So in our main program, we do whatever. We have a struct node LL. We do whatever. At some point we can say LL equals init. We jump down here, we allocate space for a struct node, we set up the fields, we return temp, which is the address of the beginning of that block of memory where the node is. That's the return value from init. LL is that address, which means that star LL will actually be that node. So this works fine. We could also, up here in main, just have said struct node LL. LL.data equals 42, LL.next equals null. And LL would be a perfectly fine sentinel node. But every time we want to call a function like add that needs the address of that, we have to say ampersand LL. And that gets to be a pain. So we'll declare our linked list to be a star to a struct node. Okay, so let's do our print function now. So LL is a pointer to a struct node. And we're going to have print doesn't have to return anything. So there's a short list, 2 nodes in it. So LL is the sentinel node. So we don't want to print the data field because the data field is not actually part of the list. The first node of our list is LL, whatever the next field is. So we could do something like this. Struct node star current equals LL arrow next. So I'm setting current up to be the first node of the list. If the list is empty, LL arrow next will be null. This sets current equal to null. Nothing wrong with that, no seg fault. If there's no sentinel node, this is an edge case. But we know the sentinel always exists. We know LL is not null. It's the address of this sentinel, which is present even if the list is empty. So this is safe to do. So while, that's gibberish, while current is not null. So what should we print? Current arrow data. Right, as long as this node exists, print out its data value. And then we want to move to the next node. So what does that look like?
Current equals current arrow next.
Exactly. Current equals current arrow next. Here's current. This is the thing that current points to. Here's the next field. Set current equal to that. That makes current point to this node. Go back up to the top. Current's not null. Print out current's data. That prints a 20. Current equals current arrow next. That changes current to be null. Go back to the top of the loop. While current's not null, that fails. We exit the loop. Return. And you're done. And you've seen this before. You saw this a week ago. That's your print code for PA1 also. The only difference is I threw these arrows in here. I could have just said current dot data if this was just pseudocode. And in PA1 we did something like LL bracket current dot data. When we have struct nodes that are just these two things and are stored in dynamically allocated memory, it becomes current arrow data. But the logic does not change. The algorithms do not change. The pseudocode does not change. It's just the implementation. So going forward after PA1, right, our struct nodes are just these two pieces. And we want to dereference, we use the arrow. But everything else we've been saying about a linked list is going to be exactly the same. So we'll run through the rest of the pseudocode tomorrow, but it'll look very familiar to you. All right, and then Friday I'll go through PA2, and then there's no class next Monday. So you'll have 3 days to work on PA2 and get some questions.